revision video, sorry. I'm just going to get straight through this. You've watched these videos before, you know what they're about. Let's just get started. Okay, so the very first thing is structure of the Earth. Okay, now structure of the Earth is pretty much made of the core, the mantle, and the crust on the outside. What you've got to know is that there's an inner core, right, which is the inner bit, and there's an outer core right here. This is the mantle, and this is the crust. Okay, now the thing you need to know about the crust is actually made up of loads of different plates called tectonic plates. We're going to talk about that in a second. Okay, now the Earth is actually made of iron and nickel. So right in here is a lot of iron and a lot of nickel. And because it's iron and nickel, that's why, it's particularly the iron, that's why we have magnetic fields. As you know, iron is magnetic. And that's how we can detect it with a compass. And what happens is the massive plates float on the mantle. And that's what I was talking about, the jigsaw pieces, which is what was made of the crust. Okay, and you can see these jigsaw pieces right here. And so these are all tectonic plates. And obviously, when they rub against each other, you're going to get earthquakes. When they move in a direction towards each other, like they do around about here, you get big, massive mountains like the Himalayas, etc. And when one plate goes underneath another, that's where you're going to get a lot of volcanoes. So I can show you this map of the tectonic plates, but how do we know that they're actually tectonic plates? What evidence do we have? Well, this is the evidence. This is a map of all of the earthquakes and volcanoes that we have. Okay, and you can see that actually all the volcanoes and the earthquakes have all occurred at these invisible line marks, which is basically where the tectonic plates are. And so that's the evidence that we have. So if you ever get a question, what is the evidence that the Earth is made up of tectonic plates, is where all the earthquakes and volcanoes and the mountains are basically forming. And everyone remembers the earthquake in Derby, which is really, really peculiar because we're not anywhere near a tectonic plate, which is why I thought our house was coming down rather than the earthquake. Earthquake was the furthest thing from my mind. Anyway, that's about tectonic plates. What you need to know is you need to know the upper layer, so of the crust. So we have the upper mantle, we have the continental crust. Basically, this is all the lithosphere. Okay, and that is made up of the upper part of the crust and the mantle. Okay, you can see that upper mantle and the crust over here, and that makes up the lithosphere. Okay, that's essentially all you have to know for that. Now, seismic waves. As you know, when the plates rub against each other, it makes shock waves. Okay, those shock waves are called seismic waves. Okay, now there's two ways shock waves or seismic waves can be produced. Number one is by earthquakes. Number two is by artificial explosions like nuclear bombs. So anytime one of these nuclear bombs goes off in one of these little tests, scientists will be there with the little seismometers and detecting it. Okay, and so we study these waves so we know the structure of the actual Earth. Okay, that's why we've got the liquid in the mantle, you've got the crust, and so obviously these waves are going to be traveling at different speeds, and we use one of these, which is a seismometer, and this is basically just a ball with a pen on the end, and it measures the strength of the waves. Okay, the actual paper that it does the drawing on is actually called a seismograph, and this is the actual seismometer. Okay, and it produces all of those waves. You might get like a graph like this, and you might have to pinpoint how big the earthquake was in case you just read it off the scale here. This isn't actually one. I've just realised this says volts, so that's not quite right. Okay, hot rock. Okay, now what you have to know about hot rock is that this is very, very hot rock. You can see how hot it is, and it will melt anything in its path. Okay, but what you have to know is that when it's overground, when this hot liquid rock comes on top of the Earth's surface, it is called lava. Okay, and when this hot rock is on the inside of the Earth, it's called magma. Okay, so in the Earth's mantle, that's where you've got the magma. As soon as it comes up on the Earth's surface, you've got the lava. That's essentially what's happening. Okay, so hot liquid rock, like it says, hot liquid rock is called magma when it's underground. When it's overground, it's called lava. And when all of that rock cools, it forms something called igneous rock. Now, the igneous comes from the Greek word fire, so you can really, really call it fire rock. So as soon as this hot liquid rock cools, it forms rock, and that is going to be igneous rock. So we need to know a little bit more about igneous rock, don't we? What's the difference between these two rocks? Well, If you look closely, you can see that these crystals are so small in fact you can't see them. Whereas these crystals are quite big, you can see them everywhere, can't you? Okay, like granite. So there was a difference between where these two rocks cooled. Now, basically what happened is that this rock, okay, would have cooled on the surface. How do we know it would have cooled on the surface? Well, because it cooled so quickly that it didn't get time for the crystals to form, which is why the crystals are extremely tiny. Whereas this rock, we know just by looking at it, because it's got the bigger crystals, it must have cooled underground where the crystals had time to grow. Okay, so you can see that here. All the rock all the lava, which basically cooled on the surface, that would have been this rock over here. All the rock that cooled underneath the surface, okay, would have been the granite, okay. And as it says, all the rock that cools above ground is called extrusive igneous rock. All the ones that cooled on below the surface would have been called intrusive. So extrusive as an exit, intrusive as an inside. Okay, there you go. Now, which rock cooled the quickest? Well, just as I've just explained to you, yeah, you can see that obviously this one cooled below the surface because the crystals had time to form. Whereas this one, where the crystals are tiny, yeah, that obviously cooled above the ground, where it cooled very, very rapidly. Okay, and there's basically a very quick explanation. Rocks have small crystals formed on the surface because they cooled quicker and crystals didn't have time to form. Rocks with bigger crystals formed underground where it is warmer, so the crystals had time to get bigger before the magma cooled and formed igneous rock. Okay, now, why do people live near volcanoes? Now, this happened right near Mount Vesuvius, and these people are encased in ash. So the volcanic ash came so quickly that these people were literally frozen in their tracks. It's not ice, but they were encased in this hot, really hot ash. And this poor person was praying for his life, and it obviously didn't work for him. Yeah, so why do people live near the volcanoes even though that they're really dangerous? Well, because the ash is actually really good for the soil and growing crops. So any land near a volcano is really, really prime farming land because the crops will grow so well. So why do people live near it? Well, they can grow their crops. And they think that the volcanoes, because they don't erupt every week, not even every year, sometimes not even every 100 years. Sometimes they think, actually, this volcano might not erupt in my entire lifetime. I think that's worth a risk. And as some of my students said, yeah, but if I saw the volcano erupting, I'd run. Yeah, but the ash is so fast, it will catch you. It's very dangerous. And I showed you the videos of how quickly it comes down. And why do scientists study volcanoes? So they can predict future eruptions. They're always looking for like certain warning signs that they're going to get. They do that with earthquakes as well. So if they study the earthquakes, they study the volcanoes, and if they've got some kind of indicator to let them know when it's going to erupt, that's really, really good. But it's extremely difficult to actually pull off. Okay, construction materials. Now, construction materials, as it suggests, are materials that we construct things with, like buildings. Okay, now you need to know that, well, you've got buildings that are made from construction materials. So what are the 5 main materials? Pause the video and have a think. What are the 5 main materials that we construct things from? Pause. And unpause. You didn't pause, did you? Naughty. Okay, look at the 5 main materials. What are the 5 main materials? There are things like brick, concrete, steel. You've got marble, all sorts of glass, all sorts of materials. Yeah. What are the 3 main materials quarried? Now, quarried just means dug out from the ground and used. But the 3 main stones that we quarry, okay, are limestone, granite, and marble. Now, you need to know which one is the hardest. Granite, marble, and limestone. GML. It's like JML, like, you know, the people that make all the gadgets, but this is GML in terms of the hardest. So granite is hardest, then marble, then limestone. Now, you need to know, how would you know one of those is hardest? Well, what you'd do is you would perform a scratch test. So the harder material always scratches to the softer one. So let's imagine if you had 2 rocks in front of you and you scratched them against each other. The one with the actual scratch marks is weaker than the other one that actually did the scratching. That's how you would test which one is harder. It's kind of a very, very, not very sophisticated test, but it works nonetheless. Okay, now, you need to know what these building materials are made from. So like I said, brick is actually made from clay. Yeah, so the clay is put into a hot furnace and it's baked. Cement is actually made from clay and limestone. Okay, so you get a load of clay, a load of limestone, and you can make cement from it. More about that later. And glass is actually made from sand. I remember the surprise in the class. What do you mean sand is made from? Yeah, it is. Yeah, so the sand is obviously heated up, and then it becomes clear, and it makes up glass. And iron and aluminium is made from their ores. Okay, so iron is made from iron ore. So basically, an ore is when you actually dig it out, you're not just going to get massive lumps of pure iron. You're going to get iron mixed with rock. Okay, and that is iron ore. And obviously, we have got to extract the iron from its ore. We're going to be looking at a little bit later. We're going to looking at copper ore and how we can extract the copper from its ore. Okay, so most metals come from an ore: iron ore, aluminium ore, copper ore. Okay, right, negative aspects of quarrying. Now, we've done a little bit about this, okay, but quarrying, millions of tons are quarried each year, but there are problems with it. So you need to know this might likely to be a 6-mark question. So I might talk about the advantages and the disadvantages of quarrying. Well, there are problems with quarrying, and the disadvantages are dust pollution. Imagine digging up all those rocks, get a lot of dust, and if your house lives near there, if your house is near a quarry, your house and all your windows might be covered in this horrible dust. You wouldn't like that because you'd have to clean the windows all the time. I probably wouldn't, but I'm sure some people would. You get noise pollution. Remember when I showed you the video of the massive rocks exploding? That's how they get the rocks away from the quarry in the first place. And so you get noise pollution. You wouldn't really like it if you're at home and suddenly you heard all these explosions. You get damaged landscapes. Now, the areas where you normally quarry are beautiful countrysides. And in that beautiful countryside, you've got this massive gaping hole. And so it damages all the landscape, and you used to have animals that live there. And so Mr. Squirrel and all of those other animals have suddenly lost where they live, and they have to move. So you get destruction of habitats, and they need to get those rocks somewhere, don't they, where they can process them. So you get a lot of traffic. You get all these big, massive trucks on these small country roads, and obviously you've got carbon dioxide from the lorries, and we know that carbon dioxide causes global warming. Okay. Positive aspects of quarrying. Jobs. Builds a community. So if you're living in this particular area, then you're going to have loads of people. Imagine you've got a shop. Suddenly you're getting all these quarry workers coming around and buying houses in the area because the quarry is going to be open for a long time. It builds a nice community. But it also, one of the main advantages is it provides materials for building. Okay, and like I said, limestone is made into cement. Okay, and tourism. People might want to see the quarry. Well, no, sure I would, but the people want to see the quarry, and so that might be nice. Okay, now when we're finished with the quarry, when we've dug out all the rock that we're going to dig, and we're like, no, we don't want to dig anymore. What can you do with it when it's finished? What we can do is we can cover it with soil and plant some grass, and then suddenly it just looks like a big hole that's supposed to be there, which might be quite nice. Or you can use it as a rubbish tip and then cover it with soil afterwards. Or, now this is what they've done with Carsington Water, is that they can fill it with water and then you can go fishing and sailing and stuff like that, water things. Or use it as a nature reserve and move the animals back in and give them a nice home again. So those are all the things that we can do with a quarry when it's finished. Okay. Right. This looks at the positive. I think I'm just going to go for the answers because I'm trying to make it short as possible. So advantages: builds building materials, local jobs, farming chemicals. Disadvantages: dust, damages the landscape, noise pollution, and increased traffic. Okay, so those are all the advantages and the disadvantages. Right, making cement. I know you guys don't remember this, so let's just go through this very, very quickly. So cement. How do you make cement? Okay, now cement, okay, is made by getting limestone, that rock that we just quarried, and then heating it with clay. Okay, now that cement can be made into mortar. Now the mortar is the stuff that you stick the bricks together in a wall with. So it's very, very soft, isn't it? So what you do is then you mix the cement that you've got and you add some sand and some water. And you've seen those little mixer things that those are always near construction sites. That's what they're doing. They're making mortar so they can stick the bricks to it. But they can also, with that, they can make some concrete. Now what you do is you can just add some gravel to it, okay, which is called aggregate, if you see it again, which is basically just small lumps of rocks, okay. Now what that does is it provides a structure and it suddenly becomes concrete, okay. So you guys have got to know all of that. So there's 3 different things: how you make cement, how you make mortar, and how you make concrete, okay. Cement is the first one. You get limestone and clay and you heat it together. So that's cement. Limestone and clay is cement. To make that cement into mortar, you add sand and water. Okay, that is how you make mortar. That rhymes. Anyway, and then to turn that cement, okay, into concrete, what you do is then you add the gravel. Okay, remember the flow diagram I did on the board. Okay, at the top I had cement and I had 2 arrows from limestone and clay going in. I suggest that you do this right now. And then below that I had mortar, and then I just had arrows of sand and water pointing into it. Then I had an arrow pointing downwards to concrete, and then I had an arrow pointing inwards to gravel, and that gives you a nice little flow diagram. Maybe I should have done it, put it on there, but I didn't. So there. Okay, thermal decomposition. Okay, you're all shouting at the screens right now and saying, I know what thermal decomposition is. You heat it and you break something down. Maybe not all of you. But thermal decomposition, you can see that thermal means heat, decomposition means broken down. And so there's the heat and it breaks things down. Why are we looking at that? Well, because we need to know what actually happens when we get limestone and we heat it up. Now, first things first is you need to know that limestone is something called calcium carbonate, okay, which is right there. Okay, that is calcium carbonate right there. Now, if we heat this up, what does it make? Okay, this is not the best diagram in the world, but this is calcium, and this is 3 atoms of oxygen, and there's an atom of carbon there. Okay, so it's CO3. Okay, so the bright ones amongst you, which is all of you, would have noticed that actually this little molecule over here, the CO2, is carbon dioxide. So when we get limestone, which is CaCO3, calcium carbonate, which is its technical name, gives off carbon dioxide. You can see that here. Thermal decomposition means using heat to break something down, as we've just discussed. Thermal is heat, decomposition is breaking, and calcium carbonate, this is what it is. You guys, you have to know it. So limestone is calcium carbonate. That is its scientific name. Ca, which is calcium, C, and O3. Okay, so you need to know that the Ca is calcium, the C is carbon, and the O is oxygen. How many elements does this have? Shout it out. Yes, well done. It's 1 Ca, 2 C, and O is the oxygen. Okay, how many atoms does it have? Did I ask you how many atoms or how many elements? I can't remember now. It actually has... so, as I was saying, when you have 1, 2, 3, they're the different elements. Calcium, carbon, and oxygen. How many atoms does it have? 3, 4, 5 atoms. Okay? Now, when you heat it up, the calcium carbonate is actually broken down into calcium oxide and carbon dioxide. Now, there you go, calcium oxide. Guys, you have to know this formula over here. This is calcium carbonate, this is calcium oxide where it gets broken down into, and carbon dioxide. And as you can see over here, yeah, what happens, what are the missing substances? This is going to be CaCO3. Which one of these is CaCO3? Pause the video, have a go yourself. You're not pausing, are you? Okay. So, it's actually calcium carbonate. That's what that thing is. And CO2 is obviously carbon dioxide. And there you go. It gives you a few calcium oxide. And, yeah, and there you are. Okay. So, what else do we have to know about this? Well, what else we have to know about this is that it gives off carbon dioxide. So, we need to be able to do the chemical test. This is what the experiment would look like. So we put calcium carbonate in here, heat it up, and it would give off some carbon dioxide. So how do we test for that carbon dioxide? Well, we bubble it through lime water, and we guys know this, don't we? Yeah, you get the lime water, and if it turns milky white, carbon dioxide is present. And as you can see there, this is lime water, it is clear. This is lime water with carbon dioxide in it, milky white. There you go. Okay, so review. Yeah, we know what thermal decomposition is. We know the chemical formula of limestone, which is calcium carbonate, which is CaCO3. What is made when limestone is heated? We know that calcium oxide is made, and we know carbon dioxide is made, and you need to know the balanced formula of equation, okay, of that, of not of limestone, but of that actual reaction, okay, which is CaCO3. Heat gives you CaO plus CO2, and the chemical test for carbon dioxide is lime water, and it goes milky white. Okay, now, we're not going to complete this, but these are all the different elements, okay, of, okay, so aluminium, those are all the properties. Property means what kind of things is it like. So, for example, aluminium is low density, it's strong, and it's resistant to corrosion, which means it doesn't corrode, okay, we're going to talk about that in a second. And it's a good conductor of electricity. You've got copper, good conductor of electricity, which is why you always see it in wires. Resistant to corrosion, which means that it doesn't react with water and oxygen and make something else. And it's easily shaped and it's flexible, hence use in wires. So there you go. The main use is electrical wiring and water pipes. Gold, shiny, resistant to corrosion, very unreactive. It's pretty much useless, really, apart from decoration. And that's why it's just used in jewellery. And steel, very strong, very dense. Okay, using lots of things, large structures, heavy duty engineering, cars, trains, bridges, all sorts. Okay, so they're the main properties of metals. So just be a little bit aware of this. Just have a look at this table, maybe pause it, have a read so you're aware of the main properties of the different metals. Okay, now in pure metals, the atoms, yeah, are all in nice regular lines. You can see this, can't you? Which is why pure metals, okay, are very, very soft. Okay, so if you have a pure metal and you hit it with a hammer, you can bend it into its shape, which means that iron isn't actually very strong on its own. Imagine these are iron atoms and they're all in nice regular rows. You hit it with a hammer, they just slide over each other. How do we make this stronger? What we do is we mix it with another element. Okay, and so can you see here now you've got metal A, which is a big metal, and you've got metal B. Can you see how now they are not in regular lines? And when you try and hit it with a hammer, the atoms can't easily slide over each other, can they? And so that means that this is actually an alloy, which is two elements mixed in together, or two metals mixed in together, which makes the alloy stronger than the actual pure metal on its own. Pause the video and just have a very quick read of that up there. So steel is an alloy, okay? It's pretty much iron, okay, mixed in with a little bit small amount of carbon. And that means that this, instead of just being a pure iron bridge, it is a steel bridge. The atoms are all jumbled up, which makes it very, very strong, okay? But it will rust, okay? That is the problem. And when you've got a bridge where there's lots of water around, bigger problem, okay? Which is why we've always got to paint it. Okay, now, other alloys that you've got to be aware of, okay? Now, brass. Now, brass is an alloy that is made up of copper zinc. Guys, you have to know this, by the way. Okay, so you need to know that brass is actually made up of copper and zinc, and is used in door handles, and it's used in musical instruments, right there. Okay, so that is brass. Bronze is slightly different. Bronze is very similar to brass in that it contains copper, but it has a higher amount of copper. You can see that 87.5%, and it has a little bit of tin. Okay, and bronze tends to be used in statues, etc. Okay. Solder, okay, now solder is used to stick wires together, okay, now this is a soldering kit. Now what you do is you just get the metal, which is right there, and you heat it up, and then it becomes a liquid metal, and then you can join it up together. Now the interesting thing about solder is that it contains lead and it contains tin, so those are the two metals it contains. Now the odd thing is that lead and tin on their own have really high melting points. Now, melting point means the temperature at which it turns from a solid into a liquid. So if you just try and heat lead on its own, high melting point. If you try and heat tin on its own, high melting point. Mix them together, melting point becomes a lot lower. Why is that useful? Well, that means that you can melt it really easily with a soldering iron, okay, and it turns into a liquid. And while it's still a liquid, you can put that liquid next to two wires, get the two wires to join, and then suddenly it will, once it cools down, it will join the wires together. Okay, so that is solder. So guys, please go through those three, and there's one more, which is amalgam. Okay, amalgam. Okay, now amalgam, it contains mercury and is used in teeth fillings. Okay, now there's someone's teeth over there which has got amalgam in there. I disagree with this because I think that the potentially is very, very dangerous because of the mercury it contains. Now, mercury is very, very poisonous. So I would always go for the polymer material, as you know from C1, and it tends to be a white colour, which is a lot better. Now, electrolysis. Guys, you guys are very good at electrolysis, and the reason why is your controlled assessments were on electrolysis, okay? So we're actually going to look at the extraction of copper first. So first came the Bronze Age, and as you remember, the bronze is an alloy which contains copper and it contains tin. And so suddenly, people weren't using just pure copper anymore because it was very soft. They started mixing in with a little bit of tin, and suddenly that gave rise to the Bronze Age, which meant harder metals that they can use for axes and what have you. Now, the thing you need to know about copper is you need to know a little bit of background about copper, and you need to know that copper is used in electrical circuits and is also used in plumbing. Okay, now copper, when it's dug out of the ground, as I told you guys earlier in the video, that copper, okay, isn't just a pure copper. You're not just going to go out into the countryside and find pure lumps of copper. It doesn't exist. It actually exists in rocks. And you need to know that the name, so that's called a copper ore, right? And you need to know that the name of the copper ore is called malachite. Okay, now, the ore is heated up with carbon, and this makes copper carbonate. That is the very first step that we do. Okay, so what is the formula of copper carbonate? The formula of copper carbonate is CuCO3, okay, which means it's very similar to the calcium carbonate, isn't it? So basically what you're looking at is we've got copper carbonate, but do we need copper carbonate? No, we don't. We just need the pure copper, which is Cu. Okay, so what we do is we get the copper carbonate and we heat it up and break it down. What is the name of this process? Exactly the same as the calcium carbonate when we heat it up and break it down. Shout at the screen. You're not shouting, are you? I forgot myself. It is thermal decomposition. Okay, and that's what it is when something is heated up and broken down. So, what is made when copper carbonate is heated up? It's exactly the same thing, guys. Okay, you get this is copper carbonate, CuCO3, heated up, and it makes copper oxide, just like the calcium one, exactly the same. Okay, and also when you break it down, we've got calcium oxide. Okay, and by the way, what is given off? Oxygen, carbon dioxide, again, exactly the same as the other reaction. Okay, so this is copper oxide, which is one copper atom and an oxygen atom. What do we need to do next? That's right, we need to be able to just get pure copper, sorry, from this. So we need to take the oxygen off it. How do we do that? Well, what we do is we heat it up. We need to remove the oxygen. We do this by heating up with carbon. Okay, and what gas is produced? Imagine heating this up with carbon. What is made? Carbon dioxide, isn't it? Yeah. So I know there's only one oxygen here, but it will take, so one carbon atom will take the oxygen off this, and it will take the oxygen off another copper atom. Okay, and that will give us pure carbon. Okay, and this is called reduction, by the way. You've got to know this. When you get when you remove the oxygen off anything, it is called reduction. Don't ask me why. It's actually quite a complicated question. Okay, but any time that you take an oxygen off something, it is called reduction. Okay, and this makes the impure copper a bit more purified. Okay, now, so this was the flow diagram. So malachite gives you copper carbonate. Okay, we heat it up, so the carbon dioxide is given off, giving us copper oxide. Then what we do is we heat this up with a little bit of carbon to take the oxygen off, and this gives us a bit more of an impure copper, but just it's got pure copper, but it's a mixture with the other things, and then we turn it into pure copper, and we do this by smelting. So melting copper to really high temperature uses a lot of energy, doesn't it? Can you see that this has been heated up to probably hundreds of degrees? Okay, which is why instead of heating up the copper to hundreds of degrees, what we can do instead is we can do something called electrolysis. Now, electrolysis, okay, electrolysis is using electricity to be able to separate it out. We know what electrolysis is. We've done it for the controlled assessment. But you need to know why recycling copper is better than smelting it, which is heating it up to really hundreds of degrees. Well, namely because it's cheaper, Okay, so just think of the heating bill for that. Wow. It saves resources, so you don't need to have as many copper mines. It saves energy from heating and crushing rocks as well. Okay, that's why recycling is better. Saves energy and no energy needed for heating and crushing the rocks and digging all those mines, etc. So, electrolysis.